What are we going to do today? I started writing a small command for benchmarking hardware. So we talked about it on the Pinball project stream, and yeah, we just did it via the log file, but I wanted to follow up on that. So what I came up with basically a new command in MPF, and it's called MPF hardware test. Looks like this: MPF hardware test. And if you execute it, it will test the hardware you just got connected. Normally it will ask you if you're certain, or it asks you, but I uncommented like the prompt where you have to confirm it, because during development I run it quite often, so I didn't want to type yes every time. And what it actually does is it measures the latency between pulsing a coil and an input reacting. And that's what is just running here. Oh, and now it got some bad messages, but that's because I was trying something. So this will probably not finish, I guess. But what I do, it's like you can see that here. I connect those coils here to the input next to it. You can make this large here. So let me see if I can focus it. Now it focuses. So I connected this coil here, this coils, to the input on the same wing on the Open Pinball project. That's my test hardware here. And that's connected via USB to my PC. And I pulse one of the drivers, and then I measure how long it takes for this input to react and to get to MPF. So that's what I'm trying. And this is how this looks. So let's restart it and try it again. I increased like the poll frequency in Open Pinball project to see if the values change. They certainly change, but if you go too high, at some point it becomes unstable, because, well, you're sampling like the too high frequency for the bus. So currently I'm sampling at 1 kilohertz, so that's quite a lot. But this time it actually worked. And we can see that I do 3 runs. First one is like I pulse for 53 milliseconds, and I went with this odd number because like normally hardware samples at a certain interval, like every 10 milliseconds or 100 hertz. And if you just go for like 100 milliseconds, then you can just fit exactly this pattern, right? So you just do like, you exactly go like it. First sample, second sample, third sample, so it will be perfectly sampled. Or you could always be unlucky, right? So you could be always like 5 milliseconds off in the sample. And this with this odd number, so like maybe like prime number would be nice, or something uneven. It's unlikely that the hardware is using exactly 53 milliseconds. And there's also no divider. So it's not like if you go with 20 milliseconds, it could be also 5 or 10, because those are dividers by the are equal. Yeah, basically they are prime factors, or they're prime. Maybe they are factors at least, yeah. And that's why I go with 53 milliseconds, 23, because it's a cool number, and 13 milliseconds. And then afterwards it goes for a random pause, a few milliseconds, so that we get like some randomness into it. And then I measure how long it takes after the pulse to for the input to become active. And that's like I calculate the mean and the median. So mean is basically the average, and the median is like, hey, how you doing? Yeah, then the median is like if you just put all the numbers into a list and you take and sort them, the number in the middle, that's the median. So those should be close, otherwise there's like a bias in some direction. So that's statistical stuff. And then I got the minimum, the maximum, standard deviation, and variance. And standard deviation and variance just say like how much how uniform are the values, or do they all fall into a small window or in a large window, and the average is just very far away from the outliers. So that's what it says here. And you can see in this case like min and max is like it's a huge spread here. And that's probably partially because I'm streaming now and the PC is encoding, so the number's a little bit better when the CPU is idle. But you can see that it's generally working. So for the Open Pinball project, like the latency is around like 10 milliseconds. If I go for like 10 milliseconds here for pulses, then it falls into the sampling rate, and it's usually the average latency is better. But here you can see like really artifacts. So like it's between 6 and 21 milliseconds latency. So that's a lot. So there's a lot of jitter here. And that's also why standard deviation is quite high. So we can run it again with like the default 100 Hertz. So it's like, so we can change that and we can play with different values. And now you will see that like, if we pulse 13 milliseconds, that's a little bit more than the sampling frequency. So that's, so we should always see the pulse, but it should be off by plus minus 5 milliseconds because we are sampling every 10 milliseconds. And in average, we're like 5 milliseconds off. And let's see how that turns out. That's odd that it got like 5 milliseconds min. That's for the latency, that's fine. It's just not the duration. So I'm also measuring like the duration of the pulse, so to see if it's actually correct. Like if we are pulsing 53 milliseconds and it would be an average like only 50, then I don't know, maybe inputs would come on faster than they go off or something. That should not happen usually, but we can measure that. And if we look at the old values here, like it's pretty close. We pulse 53 and it's a little bit shorter, but it's super close, but the outliers are weird. So something isn't perfect here. So sometimes, yeah, I mean, this can happen. So if we pulse 13 milliseconds, we sample every 3 milliseconds, we can just miss it, and then 10 milliseconds later to measure, yeah, then it can be like 4 technically. We can lose up to 5 milliseconds, and that's what we are also seeing on the minimum here. And we can add like another 10 milliseconds here for the worst case, when we just got the beginning and we lose or we miss the end by a few milliseconds. So yeah, we can see that here. But in average, it's still okay. So that's because that's how sampling works. And now it somehow got, I don't know, maybe got stuck. Let's rerun it. So yeah, that's what I wanted to show. Next would be like rules. So we would have to write a rule where we basically connect the input of the, now we got one coil which activates another input, and that then based on that input we activate a hardware rule which then pulses another coil which is connected to the next input. The first coil connected to the first input, which triggers the rule. The rule then triggers a coil which is connected to an input again, so we can measure like the latency of the rule. We did this in the last stream, but I we did it basically on the fly, and I think now it didn't work on the stream, so but I tried it later and it worked. So let's see that we can now get this professionally done. So I think, did I do? So what did I do? I created like a new config section, which is called hardware test, with coils and switches. And you need basically to connect 2 coils to 2 switches. And that's like coil 2 and switch is test, C coil 2 and S test 2, and coil 3 and switch 3. And we can also test this manually if you want. I don't know why this is not caching for some reason. Maybe I'm missing something. So I created a bit of code which activates a rule. Yeah, this works. So what you can see now is like at pulse coil 2, which is connected to switch test 2, which becomes active here. But also I enabled a rule, a flipper rule, which is just shown here, which activates with switch as test 2 and then pulses the coil 3, which is connected to switch 3. And we can now see that they both activate and inactivate almost at the same time. And we can look into the log now, what the latency in this case actually is. So we got the 17th, right? Do we have the 17th? No, we got the 18th already. And now we can look like they got, yeah, they became active at the same time. It's probably because of sampling. So we yeah, I mean it makes sense because they are sampled at the same time. So it's at least it's fast. It's faster than what we can observe. So that's good already. Yeah. So what I'm going to do is like write some code to create this rule, and then measure the same stuff again, which we just measured. Yeah. So I mean, at least we know that it's working. That's good. And now you can see it blinking, that because the rule is still active, and the second switch, the switch 3, is connected to this LED. So you can see it measuring the hardware on the video. So and these pulses are maybe too short, so that it won't see them. Probably. Let's try. Probably the stream just makes it a little bit too jittery, so that we're not so that it misses like a pulse and then the measurement stops. Maybe I should add timeouts. Always a good idea. See, and that works. And yeah, I mean, I missed those again. That's bad. But maybe let's comment this out for the stream, and I will measure it afterwards. I mean, you should measure with like with an idle PC, right? But still, in general, it's working. And now we just have to write a method which measures like pulse and then afterwards the second switch, right? So what I did here is like I built two lists for latency and for pulse duration, and then basically let's do a second one for pulse 2 duration. What would we call it? Yeah, pulse 2 duration and latency 2 for like the latency up until the switch became active. Let's call it rule latency and rule duration, rule pulse duration. And so I run a loop with 100 iterations here. And first I take a timestamp, then I pulse the coil, then I wait until the switch becomes active, take a timestamp, wait until it becomes inactive, take a second timestamp, keep a random time, and append the times to my histogram list. And what we will do now is like basically the same, but after the first switch became active, we also wait for the second switch to become active. And let's take a timestamp, and then we do same thing for like becoming inactive, and then we just calculate the values. So normally I'll start to first switch activation is my latency, and now I take I'll start to switch 2 active for the rule latency, and I take rule pulse duration, basically the difference between the timestamps of the switch to activation and switch to inactivation. And now we run all the statistics stuff. We just copy and paste that here. Rule pulse duration. Forgot to call append. And then all we have to do is like actually write the rule. So we have to write the rule in code without the flippers. See. And we can try it once because the rule is now still active in the hardware, and it for some reason isn't cleaned on startup. I'm not sure why this is. Maybe related to my firmware version. And we got the rule latency. And now test repeated pulses with rule. And we will just run those two, and let's see what we get. And it's testing. Doesn't look so well, because it just stopped quickly. Not so good usually. So what would be the reason? Wait for switch 1 active, 2 active. I mean, we can try without the wait. And it seems to pass. Good. So now they should be basically the same because there's nothing happening. So that's working. Let's see why this could be. Yeah. So we have to tell, I mean, I guess in most cases it will be just already there. And that will now probably also the case here. And now I tell MPF, so do not wait for an explicit change. I mean, if it already reached the state and also just finish. See, yeah, that looks a lot better. And now it should measure something more reasonable. See, get, but we just saw that it's actually not. There shouldn't be a difference here. See, maybe in some cases, maybe like in 10% of the cases. Indeed. So like we got a certain latency, and the rule latency is a little bit more because why? Ah yeah, because we might sometimes miss, like we might not always read them in the same polling slot, so they might be off a little bit in some cases. And pulse duration is like, okay, it's 100 milliseconds because that's what's configured in the rule. That's what I configured on the coil. So that makes sense to me. So that seems to work, and but like a small difference here for some reason. Yeah, by roughly 1 millisecond. Interesting. Interesting stuff. See. So now all we need to do is like writing the rule. So currently we're not writing the rule, and I guess the way we're doing it is like we just put a flipper configuration into this hardware test stuff, and then we are activating the flipper, because otherwise the code might break in the future, and I don't like that. So now we got like flipper device here, so like this device, and we can simply call enable, and it will write all the rules for us. Because otherwise, I mean, this code might break in the future, because you can see what it does. It creates a lot of settings stuff, hold settings, pulse setting, repulse settings, and we sometimes add more parameters here when we add more support in hardware, and we might then miss like the hardware test command. So I'm not duplicating the code. Instead, I'm just calling into the flipper device, and that will be the way we can benchmark it. And that's actually also better, because at the end you will use this flipper device anyway to activate your flippers, so that will be the rule you're typically using. And so it makes sense to actually benchmark this way. So I mean, we probably have to document that you have to use the same coils and switches in your flipper device, but other than that, we just call enable here, and at the end, when we're done, we call disable again and see how that works for us. Now, in my configuration, so what happens now? Usually, it would recommend the setting here, but for that to happen, I have to restart like the IDE. And now, since I changed the specification, it will now say, here, flipper, and now it also knows the flipper device, which is just here. And yeah, maybe we can also validate that we're using this. Yeah, I guess we can do that. We could validate that it's using the correct, switch and coil. Yeah, we'll do this later. Let's just test it first. Yeah, had that open. Okay, let's try. So It will work once at least because the rule has been active before. Let's see what happens on the second time. When it disabled it at the end. So it's yeah, measured the first one. Didn't get any unexpected results. Let's see the second one. Also kind of expected. That works in general. Now we'll run it again. And it works again. Nice. That's very good. And now we can play basically with the poll hertz here and see if that makes a difference. I don't know. Maybe. That's basically how often MPF will poll the switches in the Open Pinball project. And more polls means more like bus contention because we're sending more useless. I mean, yeah, it depends on how you define useless, but more messages in general, and that will saturate the bus somehow. So this is for 200 Hertz, and we can run it again for like 500 Hertz. 500 shouldn't be an issue. I mean, 1000 sometimes I get bus errors because it's constantly sending messages. And we run into like CFC errors, so like checksum, wrong checksums, which MPF can recover from in the Open Pinball project, but still you're then losing messages. So this actually made it worse. Interesting. Probably because MPF is doing more in this case. So we really, yeah, that's just something sometimes happens. The standard deviation, the variance, standard deviation definitely got a little bit better. I mean, not much. But I mean, we got this latency always. We got like 1 milliseconds to 2 milliseconds more for the rule latency. And I guess if we sample more often, then we see more of the latency, right? Yeah, it's true. I mean, if we sample only once per second, they would be like always at the same time. But if we sample more often, yeah, then we see the difference, right? Yeah, that makes sense. Maybe we should like, I mean, the rule latency would be the latency between the first switch and the second, right? So maybe we should calculate it this way. That would make more sense. So the rule latency is a switch 1 active versus switch 2 active, right? So let's do that again, and we should see what we get. So let's see how this turns out. So this is now 500 Hertz, so basically a resolution of 2 milliseconds. And we can now see how fast the rule latency is. It's 2.5 milliseconds. Okay, that's basically it's one sample afterwards, and sometimes two afterwards. And yeah, like the minimum is basically if we get it at the same time, that's probably Python latency. And this is the median is just one sample afterwards. So it's probably like a millisecond or something for the rule in reality. But we would have to use a scope to find the real latency, which we actually could also do. So the latency in general is the same, similar. Duration is good. This is also good. Yeah, I'm happy with that. Really. Let's go back to the default, and now we might actually see like near zero latency, because we usually would get both pulses in the same sample. Okay. And yeah, I mean, I will commit this command to MPF, and then like you can run it on your own hardware, on your own setup. So this is influenced by the operating system, by load of your PC, power of your PC, whatever's new USB, and so on. Firmware, a lot of factors. So benchmarking is always hard, but then you can run it on your setup. So yeah, now the rule latency became less, because in most cases it will be in the same sample. And the mean latency is also higher because we're sampling less often. Yeah, we can now try run 1000 again, and that should actually give us better reality. Let's see what it actually is. I guess because internally this hardware also has some kind of sampling for the inputs, so I don't know how often that is for the rules. So okay, at 1 kilohertz the rule latency is also around 2 milliseconds. I guess it's around 2 milliseconds. So that makes me suspect that the hardware is sampling at like 500 hertz internally. That would account for like 2 milliseconds latency, or like an average latency of 2 milliseconds. Then it might also sample at 250 hertz. 250, because like it's the average, right? Maybe you will know. So if I ask you, you will know. So I guess unless you got some questions, and there are not so many people attending to ask questions, I don't know. That's it for today. I'll wrap this up here and just push the code up to MPF repository, so you can run it on your machine if you want, just to get like an idea how fast it is, and how large the latency on your setup is. So yeah, that's from me. Have a great night. See you next time, and thanks for watching.